Hello, everyone. Today we're going to go into the other organic compounds besides the hydrocarbons. So there's a bunch of other different types of organic compounds, but you have some reference tables to help you out. So it's not that bad, but you really want to try and use the reference table that we're going to talk about today as much as possible because it really helps you out. So what are the other organic compounds? So it's an atom or group of atoms that replaces a hydrogen in a hydrocarbon. So these all kind of build off of the hydrocarbon. So that's why we started with those. And now we're just going to kind of build off of those and make all these other types of organic compounds. So these functional groups give the compounds their functions. So they're distinct physical and chemical properties. That's why we call them these functional groups. They give them their function. So where can organic compounds and their functional groups be found? Table R of your reference tables. So take out your reference tables and go to table R and just take a quick look at it. And we're going to walk through that today and use that to help us out. So here's table R. So there's a lot of information on here. We're just going to kind of work our way down through all these different types of other organic compounds. And this is what we want to really look at here, the functional group. You don't really have to worry about this general formula column, but the functional group column here is really helpful. That's going to help us identify. And then we're also going to want to focus on the examples because the examples are really helpful because it kind of gives us an idea of how to name them and makes things a little bit easier for you. Okay, so let's go through this stuff. So before we get into each individual type of organic compound, let's look at some of the things that are the same from one to the next. So what are our common rules? So what does the R represent in the general formula first? So that represents the hydrocarbon chain bonded to the functional group. So you're going to have these branches of carbon chains coming off of the functional group, and that's just what that R represents because that can change. And like an R prime, if you see that there, is a different length carbon chain. So we don't really need to worry about that too much, but that's just showing you the variations that you can have. Just like with hydrocarbons, you can have all different length chains. Same thing applies to the other organic compounds, and that's going to change their names. So what are our common rules? 1, each functional group gets a number for position in the carbon chain. So just like when we did the double bonds or the branches in the hydrocarbons, it's the same thing here. We use a number for position. So try and see how everything's tied together, and that makes it a little bit easier. So, and remember, same thing applies here. We're always going to give it the lowest possible number. So you're always going to start from the side of the compound that gives you the lowest possible number, just like with the alkyl groups or the double or triple bonds. Okay. Number 2, multiples of the same group get di, tri, etc. So just like with the branched alkanes, multiples of the same group got di, tri, whatever. Okay. So all these things are carrying over into this topic. So try and again see the similarities, and it makes things a lot easier. So now let's start going through the different organic compounds. So number 1, what is a halide? So a halide is where a halogen, our group 17s, replaces a hydrogen in an alkane. So we're taking an alkane and we're just taking out an H and replacing it with a halogen. Pretty simple. So how do I name a halide? So the naming varies from one compound to the next, but again, there's a lot of similarities to what we've done already. So you want to really try and see where those lie. So how do you name a halide? So you're going to place the root of the halogen in front of the alkane name. All right. But now remember our rules that we talked about on the last slide, those common rules. Number for location and multiples of the same get di, tri, etc. So those are going to carry out through all of our organic compounds. So there are exceptions, but I'll show you how to kind of use the reference table to help you out with that. So let's look at some examples. So copy this down. So we've got a 4-carbon hydrocarbon, but now instead of a H, we've replaced that with a chlorine here. All right. So how would we name this? So we put the root, and now what are the roots? They're right on table R. So look on table R, right here. Fluoro, chloro, bromo, iodo, right? Those are our roots for our halogens. So it's all right here. Use the reference tables, right? This is going to help you out big time. So chlorine is chloro. So now we put that root in front of, so it's chloro. And then we have a 4-carbon alkane. So you should be able to name that, no problem. We would call that butane. So this is all just kind of one word. Chloro, butane. And don't forget number for location. So where on the carbon chain is that chlorine? So 1, 2. So remember, we always want to start from the end that gives us the lowest possible number. So it's not 1, 2, 3. So it's 2 chlorobutane. That's it. Really simple. So don't overcomplicate these. Don't overthink these. It's not that bad. So let's look at another example. Now I have 2 halogens. I got a bromine here, and I got a bromine here. So how am I going to name this? Well, remember, we use our number for location, and we got to use our root off table R for our halogens. So bromine is bromo. So now where do I have a bromo? I got a bromo on the 1 carbon and a bromo on the 2 carbon. So now, because they're both the same, we don't say them separately. We say them, put them together and put a di in front. So it's dibromo. So now where do I have those? This would be on the 1 carbon, comma, 2, on the 1 and the 2 carbon. Dibromo means there's 2 bromines. And then it's on, same thing, a 4-carbon alkane, butane. So that's 1,2-dibromobutane. So there are 2 bromines, one's on the 1 carbon, one's on the 2 carbon of a 4-carbon alkane. So it's not so bad. So again, every branch gets a number. Every functional group gets a number. So where are they? 1 on the 1 carbon, 1 on the 2 carbon. So if we had one over here, it would be 1,3, right? If we had one on the end, it would be 1,4. So whatever end you start counting from with your carbons, remember you want to stay consistent and keep those numbers the same. And then we could even have 1,1, because if I put one down here, that would be 1,1. Doesn't matter which side it's on of the carbon, top or bottom. If it's whatever the number is, that's fine. So even if I put one up here, that would still be 1,2. Right, it's the same thing structurally, because remember, these things can twist and turn. I can move that around, and it's not structurally different. All right, so now let me show you one more quick example here. What if we had more than one, but they're not the same halogen? So let's say I had 1, 2. We'll do the same thing, 4 carbons. So let's draw this down here. So fit this in your notes somewhere. So let's say I have a bromine here, and then I have a fluorine over here. H, let's put our H's in. Keep them capital. All right, so now what do we call this? Well, now I've got a bromine here, and I've got a fluorine here. So now they're not the same halogen, so we treat them like different branches. So, and you just always want to start with the one that's the lowest number. So where are they? One's on the 1 carbon, one's on the 2 carbon. So on the 1 carbon, I have a bromo. And then on the 2 carbon, I have a fluoro. And again, it's still a 4-carbon alkane. So it's butane. So this would be 1-bromo, 2-fluorobutane. That's about as hard as that's going to get. So those are the halides, right? So now let's move our way down and go to the alcohols. So the alcohols, what's our functional group? Oh, sorry. So our functional group is just an OH. So we call this OH a hydroxyl group. So hydro and oxy. It's got hydrogen and oxygen in it, right? So how do you name an alcohol? So we take our prefix, based on the length of the carbon chain off of table P, right? Prefix plus anol. Alcohols are going to end in anol. And that's pretty much it. Not too bad. Now, but remember our common rules. We use a number, multiples, di, tri, all that stuff. So let's take a look at some examples. So here's our first example. So notice it looks really similar to what we've seen already, but the difference is, here's our functional group. We've got an OH here. So again, think back to our rule of how to name. Prefix plus anol. So 4 carbons is bute. 4 carbons is bute. And then we end in anol. That's it. And now remember our common rules. We need number for location. So our functional group, our OH, is on the first carbon. So it's 1-butanol. That's all. So now let's take a look at something here now. This we call a dihydroxy alcohol. So it has 2 OHs in it. So you'll never have to draw this or name this, so don't worry about it. But sometimes it does show up, and they do show them to you. So just understand that it's just another type of alcohol. But if we were to name this, it would be something different than what you would think, right? You would think it would be, okay, on the 2 carbon, we have a functional group. And on the 3 carbon, we have a functional group, our OHs. So it's 2, 3. But now you would think, okay, there's 2 of the same. So you put a di in front and say it once. So it would be dibutanol, but that's not right. For some reason, they changed it up, and you say the name of the alkane. Then you put your di, and then it ends in all. All right, so don't worry about this. You'll never have to draw it or name it, but just be aware that you can have more than one OH on a hydrocarbon, and that makes a dihydroxy alcohol. You can have 3, you can have a trihydroxy, and so on. So you can have more than one hydroxyl group on a hydrocarbon, and it's still considered an alcohol. That's all I want you to get out of that. Right? So this is the one that we're really going to focus on, just the single OH. That's all I'll ever ask you to draw or name. So our alcohol is soluble in water. So remember our general rules that we went over in the beginning of this unit. We said that most organic compounds are insoluble in water, but alcohols are soluble in water. So they are an exception to the general rule. And remember why? Because they are polar molecules. So they're polar molecules. They're asymmetrical. So they are soluble in water because like dissolves like. So remember those things we learned back in solutions. So do alcohols conduct electricity? No, because they do not have free moving charged particles. So even though they're soluble in water, they are still covalent compounds. They do not have charged particles, so they're not going to conduct electricity. Next up, we have the ketones. So for the ketones, our functional group looks like this. It's a C with open ends off each side, so that represents those more carbons coming off of it, but then we have a double bonded O coming out of the top. So remember, carbon 4 bonds, 1, 2, 3, 4. So we have this double bonded O. So we call this a carbonyl group, right? This is our carbonyl. And now there's something also I'm going to show you that's similar to the condensed structural formulas that we talked about earlier in the unit. So when you look for that sequence of elements, you want to look for a COC, right? COC. So write that down, box it in for now, and I'll show you how that helps out later on. So COC, so I call that the rooster. It's a cock-a-doodle-doo, right? So there's your COC. So you look for the COC, and that's how you know it's a ketone. And I'll show you that in examples. So how do you name these? Again, just like the alcohols were prefix plus anol, what's going to generally change is the ending. So these are prefix plus anone. So ketones end in anone, alcohols end in anol. So it's that simple. And remember, you have table R to help you out with this stuff, so it's not too bad. So here's an example. So here's our so copy this down, and we'll take a look at it. So here's our functional group. All right, that's our carbonyl group. So how do we name this? Well, it's 1, 2, 3, 4, 5 carbons. So our prefix off of table P is pent. And ketones end in anone. And then where is our carbonyl group? Where is our functional group? We need number for location. Don't forget about our common rules. So which carbon is this double O on? Lowest possible number? 2, right? So we got to start from the right. 1, 2. It's on the 2 carbon, not the 4 carbon. There's no such thing as 4. We always start from the end that gives us the lowest possible. So that's 2-pentanone. Okay. So this will be called 2-pentanone. So on the second carbon, we have our double bonded O, and ketones end in anone. It's a 5 carbon chain, so pent, and that's it. So it's 2-pentanone. And notice, right, we don't have an H down here because this is already giving us 4 bonds. 1, 2, 3, 4. Now, what do I mean by the condensed structural? So what does this look like if we drew it as a condensed structural formula? So, well, first we've got 3 carbons. First we've got 3 hydrogens attached to our first carbon. And then it's CH2. And then another CH2. And then we have our COC, that double O coming off that carbon bonded to another C. And then that last carbon has 3 H's on it. So this is our condensed structural. And here's our COC, right? So that's how you would identify this as a ketone if I showed you the condensed structural. So you'll never have to draw this, just like I said with the hydrocarbons, but you want to be able to identify the types of compounds with these condensed structurals. So next up, the aldehydes. So the aldehyde functional group is just like the ketone. We have a C double O. It's that carbonyl group. But instead of having 2 open ends, it only has 1, which means it's going to always be on the end of the chain. So we'll talk about the difference between the aldehydes and the ketones in a minute. So what's our sequence in the condensed? It always spells Joe. So look for the CHO, CHO. So how do you name aldehydes? So it's prefix plus anal. So pronunciation is important here. It's pronounced anal. So aldehydes end in anal, ketones end in anone, alcohols end in anol. So you're seeing these differences, and it's pretty consistent in terms of how they change, right? So here's an example. So 4 carbons, but now our double O is on the end here. So there's our functional group. So boxing it in often helps. So that's why I tend to do that. So we would call this butanal. So this is butanal. Butanal. That's it. So 4 carbons, but, and it's an aldehyde, so it ends in anal. Now, I don't need a number here, so we'll talk about that in a minute, why I didn't put a number here. So how does this look as the condensed structural? Well, we've got a CH3, then a CH2, then another CH2, and then our CHO. So there's our CHO that we would look for in the condensed structural. All right. So why don't the names of aldehydes need numbers to show position? So because it's always on the end carbon, right? It's always on the end carbon, which we would call the number 1 carbon. So it would always be 1. So if it's always going to be 1, there's no need to put it. So it's kind of redundant. So we just leave it out. So that's why we don't need a number for the aldehyde. So our common rules, number for location, but sometimes we don't need the number. And this is one of those cases because it's always on the end. It would always be 1 carbon. So we don't put the 1. So what's the difference between aldehydes and ketones? So they're both very similar. So let's look at our difference here. So let's look at a ketone versus an aldehyde. So in a ketone, that double O, that double bonded O, is always on an interior carbon. So it's always on a carbon inside the chain. So it's not on one of the end carbons. It's always on a carbon inside the chain. So for the aldehydes, we just said the double O is always on an end carbon. All right, so that's the difference between them. They're both the carbonyl groups, that's C double O, but in the ketone, it's always on the interior carbon, and in an aldehyde, it's always on an end carbon. But remember, there could be more than one interior carbons, so that's why you still need a number for the ketones. So a good way to remember this is think of the alphabet. Whoa. So think of the alphabet. A is the first letter. So that double O is always on the 1 carbon. And K, so A for aldehyde, and K is an interior letter. Okay? So aldehyde, first letter, A, always on the first carbon. K, interior letter. The carbonyl group is always on an interior carbon, right? So that's the differences between them. So they are very similar looking. And they're right next to each other on table R. We'll talk about that at the end here. So next up, the organic acids. So my functional group here is, we have a C double O, just like in the aldehydes and the ketones, but we also have an OH. So this is a carbonyl group and a hydroxyl group kind of combined. So we call this a carboxyl group. So sometimes they call these carboxylic acids. It's another name for them. Instead of organic acids, sometimes they also call them carboxylic acids because they have that carboxyl group there. So how do you name these? So these are really easy to name. It's prefix plus enoic acid. And our sequence of elements in the condensed structural is going to be COOH. So we look for that in the condensed structural, and I'll show you that. So here's our example. 2 carbons. So here's our functional group. Here's our carboxyl group, our COOH. So we would call this 2 carbon. Now when you box it in the functional group, don't forget about the carbons that are part of the chain. This is still 2 carbons in the chain. It's not 1. It's 2 carbons. So that would be eth, and then these end in enoic acid. Done. All right. So do we need a number here? No. So why not? Because same thing as the aldehydes, this is always on the end carbon, so it would always be 1. So we don't put the 1. So now let me show you a little trick here about that. Let's look on table R. Remember, use table R as much as possible here. Look at the examples here. So here's ones we've done already. So we've done all these already. So when do you need a number? Use the examples. So the rule is use number for location. But like I said, sometimes we don't need a number, but that's where the examples help you out. Look at the examples. If an example has a number, you need a number. So halides, number, always need a number. Alcohol, number, always need a number. We didn't get to the ethers yet. I'll come back to that. Ketone, number, always need a number. But look, aldehydes, no number. Organic acids, no number. So those are the ones you don't need a number. There's other ones too, and we'll get to those as we go. So just, that's a good trick to remember. Use table R. If the example has a number, you need a number. What is the number? Location. If the example doesn't have a number, you don't need a number. All right? So that's that simple. So this is ethanoic acid, 2 carbon organic acid. So what would this look like as the condensed structural? CH3COOH. So here's our carboxyl group, our COOH that we'd be looking for. So why are organic acids classified as acids? Because what's the definition of an acid? Think back to our Arrhenius definitions. Because they produce H plus ions in solution in water. That's what makes them an acid. So we've seen these before too, back in acids and bases. So here's an example. Here's our ethanoic acid, aka acetic acid. It's vinegar. Right? We've talked about this before. So it looks like this, CH3COOH. So when this goes into solution in water, remember this is the H that pops off. So when this goes into solution in water, it's going to break up into we're going to get CH3COO. That's our acetate ion, plus our H plus. So it's still an acid. Acids produce H plus in solution. So that's why organic acids are classified as acids. Do they conduct electricity? Yes. So remember why? Because they have free moving charged particles. So acids are electrolytes. They break up into ions and they conduct electricity. So next up, the ethers. So the ethers and the esters are a little bit weird, but they're not too bad. They're just different. So we'll do the ethers first. So for the ethers, your functional group is simply an O, but instead of coming off of a carbon, it's inside the chain. So it kind of breaks up the chain. And we'd see that as an OC in the condensed structural. And I'll show you what I mean by that. So how do you name an ether? So let's draw the example first, and then we'll use this to help us out and go through the steps. So first thing you want to do is you name each branch as an alkyl group. So those are like our branches coming off of a branched hydrocarbon. So we name those alkyl groups. So if the branches are the same length, we're going to use di because those are multiples of the same branch, same size branch. So just like in our general rules, use di, tri, etc. for multiples of the same size branch or the same functional group. And then they end in ether. So how do we name this? So you kind of treat the O as if it's kind of the main chain in a branched hydrocarbon. So what do we have coming off here? We have a 1 carbon branch, which I would call a methyl. And then I have a 2 carbon branch, which I would call ethyl. And then this is an ether, so it ends in ether. That's it. So it's not that bad. And you don't need a number. So look on table R. The example doesn't have a number. You don't need a number because we're building off of that central O. So we don't really need a number here. You could still recreate this without the number. And that's the important part. So methyl, ethyl, ether. Generally, you name the shorter chain first. But if you call this ethyl methyl ether, I wouldn't mark that wrong because you could still draw the same exact structure with that name given. So either one's fine. Methyl, ethyl, ethyl, methyl. It's the same thing. Now, how does this look in the condensed structural? Well, we've got a CH3, and then we have our O, and then we have a CH2 and a CH3. So here's that OC that I was talking about to recognize in the condensed structural. So those are our ethers. We're going to practice all these at the end anyhow. So next up, the ester. These are probably the trickiest ones, but they're still not too bad. So esters, our functional group, it's like an ether and a ketone combined. So we're taking that central O and then we're combining with a carbonyl group. So here's our carbonyl group, COO, but then we have another O. So it's kind of like a ketone and an ester combined. And this is going to look like this, Cu. So I like to say, think of like Esther, like some old lady, and they like to pinch your cheeks and go, Coo. So Esther says Coo. So good old Wendelin Giebel taught me that one back in 1996 when I was in your place. So I'm passing that on to you. So our common uses, what are these used for? So esters are important because they're used for flavoring and fragrances. So when you go to like Yankee Candle and you buy a vanilla cupcake candle, it doesn't have pieces of vanilla cupcake crushed up and added into the wax of the candle. They are putting the esters, the compounds that give the cupcakes that scent, right? So we've recreated these naturally occurring compounds in a laboratory, and then you put that into the candle, and then that gives the candle its scent. So that's anything with like these scenting, like flowers, perfumes, that kind of stuff. So with these floral fragrances, we've recreated those esters that are created naturally by these plants or whatever, and put those into things to make them smell nice. So those are your esters. So how do you name an ester? So these are a little tricky. So draw this example here, and then we'll walk through it. So notice when you have this drawn, and you box in your functional group. So let's box in our functional group. So notice when we box it in, it kind of forms a capital L. So you're going to use that to help you name these. This is the easiest way to do it. So I'm going to put it in quotes because it's not really an L, but it's that boxed in L. The L always points towards the alkyl group. So the L points towards the alkyl group, and then the other side of the the other side of the O with that double O, with the C double O, that gets a prefix for the length of the carbon chain, plus a noate, A-N-O-A-T-E, a noate. So it's a little weird, but it's not too bad, but this is probably the trickiest one. So the L point towards the alkyl group. So a one carbon branch is coming off of that O. So we would call that methyl. All right, so one carbon alkyl group. And then we go to the other side of that central O, breaking up the chain with the double O on it. 2 carbons. Don't forget about the C inside the functional group. That would be eth. And then these all end in NO8. So again, these don't need a number. Use table R. The example doesn't have a number because we don't need one to recreate this. We're kind of building around this central O. So that's methyl ethanoate. And if we drew this as the condensed structural, remember we want to look for that Cu. So we get CH3, C with a double O and another O, and then it ends in CH3. So there's our Cu that I was talking about. So now the next two aren't that important, but they do come up every now and then. So I just want to show them to you, but we're not really going to spend too much time on these. So these are called our amines and our amides. So anything amine or amino, whatever has nitrogen involved. So for the amines, what they show you on your reference table is an N with 3 open bond sites, because remember nitrogen has 5 valence electrons. So it needs 3 more to get a full valence shell. So it wants to form 3 bonds. So these are prefix plus anamine. Like, hey, it's an amine. So it's going to end in anamine. So here's your example. So 1, 2, 3 carbons. This is prop, 3 carbons. And then it ends in anamine. And now don't forget our general rules. Where is that nitrogen on the first carbon? So it's 1 propanamine. Look at the example. The example has a number. You need a number. Number shows location. Lowest possible number. So, oh, wait. Thing. So next up, the amides. So amides is kind of like a amine and a ketone combined. So we get a C, and then we have an N. I don't like that. So amines are amides. So amides are an amine with a carbonyl group in them. So here's our COO, and then we have N, and then they'll put this up there. And this is how they draw it on your reference tables. So that's just kind of how I'm drawing it here. And in our condensed structural, that would show up as a CON, which spells con. So you got your Ku, your con, your cho, your rooster, your COC. So be able to recognize these sequences and use them to identify the type of organic compound. So these are just like the amines. It's prefix plus an amide. So like, hey, look, there's an amide. So here's our example. So notice our functional group here. So this would be called prop for 3 carbons. And then it ends in an amide. Okay? And we don't need a number here because these are always on the end too. But again, use your reference tables. If the example has a number, you need a number. If it doesn't, you don't. Now, last thing quick, I just want to show you something. This is an amino acid. You won't have to name these because the naming is different if you remember back to Regents biology, living environment. When you talked about amino acids, they had names that don't sound like what we've been talking about, lysine, thymine, whatever. So we're not going to worry about those names here, but why do we call these amino acids? Because look, we have an amine. So we have our amine group plus we have our carboxyl group. So it's an amine plus an organic acid. So we call it an amino acid. It's an amine. It's an amine plus an organic acid. So it's an amino acid. That's why they're called amino acids. So I wanted to show you that. All right. So that's it. So now we want to practice. So there's 3 worksheets here that I want you to try out. So all I want you to do here on this first one is to just tell me the class of organic compounds. So look on table R, right? What do I mean by that? Is it a halide, an alcohol, an ether, whatever? You don't have to give me the exact name. I just want to know what class it belongs to. So use your reference tables, table R, to help you out with that. So I'll show you some examples here. So look, here's COOH. So find your functional group, box it in. Don't confuse your organic acids with your esters, right? If it's C, don't just go, oh, look, there's the Ku that Mr. Z was talking about. When it's Ku with an H on the end, that's an organic acid. So look for that COOH. So I don't want you to name it specifically. Just tell me the type of organic compound that it is. So what do I mean by that? So like look at number 8. There is the Ku, right? Notice how there's no H following it. So this would be an ester. All right, so try the other ones out. Box in the functional group, and then just tell me what type of organic compound it is, and we'll go through it. So pause the video, try those out, and then unpause it, and we'll go over it. Okay, so let's look at the rest of these quick. So number 2. Here's your COC. So there's our rooster. COC means we're dealing with a ketone. Number 6, we've got OH. So anywhere that OH is, anytime you see that hydroxyl group, we know it's an alcohol. Usually it's on the end when you see this, but it doesn't have to be. Number 7, here's our COOH. That's another organic acid. Next up, number 3. See, here's our OH again. So that's an alcohol. Number 4. Oh, wait, look, here's our OC. So that's how we know we've got an ether. Number 5, here's our CHO. Remember, CHO is always an aldehyde because that double O is on the end, so that O is always going to show up on the end. Number 9, here's another COC, so that's another ketone. And then number 10, there's your OC, so that's another ether. Okay, so that's all I wanted you to do on this worksheet. Don't tell me the specific name, just the class that they belong to. Next up, I want you to draw these. So let's try drawing these out. So how do you draw them? The easiest way to do it is draw the length carbon chain and then kind of build off of it. All right. So butanoic acid. So first you got to say, all right, it ends in anoic acid. So I know it's an organic acid. And use your reference tables to help you out. So you take a look here and you go, okay, it's an organic acid. So my functional group is COOH. So use this and see, okay, what do I need to include in this compound? So any of these have to have that functional group present for it to be in that class of compound. And again, use the names to help you out here. Use the reference tables. They're kind of showing you what you got to do. If there's a number, you need a number. It's always the lowest possible number showing location. Look at how they're naming it, right? So it's a halide. Oh, it's the root goes in front plus alkane name. Alcohol, prefix plus anol. Now I need a number. Ether, name them coming off of the O. Methyl, ethyl, ether. Don't need a number. Propanal, prefix plus anal, right? Pentanone, prefix plus anone. All of the rules are right here on table R. Just use it to help you out. Organic acids, propanoic acid, prefix plus anoic acid. So you go, all right, that's easy. So prefix but, that's 4 carbons. 1, 2, 3, 4. And then we got to put our functional group. Here's our double O, OH. And then just go around and fill in with your H's. And you're done. So try the ones out. If you get stuck on one, skip it, do the rest, and then check out your answers. Check out the answers and see how you did and see where you might have made some mistakes. We'll practice these more going forward, so don't worry. So use table R. It's all right there in front of you. All right, so what are the answers here? So methanal, meth is 1 carbon. And then anal tells me it's an aldehyde, so I need my double O. And then I just got to put my H's. Don't overdo it. Carbon can only get 4 bonds. So that's methanal. It's a 1 carbon aldehyde. So notice there's no such thing as methanone because there's no interior carbon, right? There's only 1 carbon. Nobody's on the inside, so we can't have a ketone. So number 6 up here, this is a tricky one, right? So this is methyl methanoate. So when it ends in that anoate, we know it's an ester. So you got to, with the esters and the ethers, the easiest way to do those is to draw the functional group first and then build off of it. So those are a little bit different. Generally, you just write your main chain and then add in the functional group. But for the ethers and the esters, draw the functional group first and then build your organic compound off of it. So what's our functional group? For an ester, COOO. So now let's go up here, right, and remember our rules. So it says methyl. So the L, right, the L of our functional group points towards the alkyl. So I'm going to put a methyl group over here. and then methanoate. So the other side of the O gets one carbon, and that's it. But don't forget about the one in the functional group. That counts. That's our one carbon. So then all I got to do is put an H there. So that's methyl methanoate. If you drew that right, then you're doing great. Those are the trickiest ones. So number 7, 3-pentanol. So pent is 5 carbons. 5. On the third carbon, we're putting our prefix. It ends in anol, so it's an alcohol. So our prefix is OH. And then we put our H's all around. I'm going to skip the H's just to speed things up here. So that's 3-pentanol, because I can have 2-pentanol, I can have 1-pentanol, can't have 4-pentanol because that's just 2 again, lowest possible number, right? Can't have 5-pentanol because that's just 1 again. So always remember, lowest possible number. Number 3, methanol, 1 carbon with the OH. Put it anywhere you want. It's always going to be coming out of the 1 carbon. Doesn't matter if it's here, here, or here. And then these are just H's. All right, next, butanone. So anone means we're dealing with a ketone. So but, 4 carbons. Now, ketones get a number, right? We look on table R, has a number. Where do I put it? Well, don't get confused here and don't think that no number means we put it on the end. It's always got to go on an interior carbon. So I'm going to put it right here. And then I put my H's all around. Don't put an H here, right? Carbon can only get 4 bonds. So now how come I didn't call this 2-butanone? Because look at my options of interior carbons, here or here. Based on our rule of lowest possible number, any carbon I put this on, it's going to be the 2 carbon, so you can drop it. So remember what I've said back in the hydrocarbons. Sometimes the chain is so short, you don't need a number. But when in doubt, put the number. Use table R. If the example has a number, put the number. So writing 2-butanone would not be wrong, all right? So don't put it on the end, because then that would be butanal. That would be an aldehyde. So remember the difference between your aldehydes and your ketones. It's a very slight difference. So don't make those mistakes. So next one, ether. So the ethers are actually pretty easy. So just like the esters, start with the functional group. So here's my central O, and we just want to build off of it. So remember, the di means there are 2 groups of the same length. What are they? Ethyls. So there's an ethyl on one side and an ethyl on the other. That's it. So these are weird, but they're actually really easy. You just build off of that central O. So we don't call this ethyl-ethyl. It becomes diethyl. If these were different lengths, then we would name each branch separately. Number 8 is methanoic acid. So it's a 1 carbon organic acid. That's it. Propanal is a 3 carbon aldehyde. So what's an aldehyde? We put that OH on the end. Get your functional groups right off of table R. H's, and we're done. That's propanal. So remember, we don't want to put this here because then that would be propanone. So last one, 10-pentanone, 5 carbons. And then where do I put my functional group? That's COO on the second carbon. And then put your H's all around. And that's 2-pentanone, right? I could have 3-pentanone. No such thing as 4-pentanone, because that's just 2 again. And there's no such thing as 1-pentanone, because then that would become pentanal. Last one. Now name the structures that are given. Right now, I actually want you to name them, not just tell me the class. So remember how to do this. Box in the functional group. Identify it. So you go to table R. And you go, okay, what is this? OH, it's an alcohol. So prefix plus anol, and it has a number, so I need a number. So eth is 2 carbons. So this is So this would be ethanol. And now where is that double O? It's on the one carbon. So I could call it 1-ethanol, but realize I don't have to put that one, because anywhere I put that OH, it's going to be on the one carbon. If we're starting from the end, that gives us the lowest possible number. So you could just see it called ethanol, but use table R. If the example has a number, you can put the number. That's fine. Number 2, here's our functional group, our carbonyl group. So we know that's a ketone. So this is propanone. And where is my functional group? On the second carbon. But again, just like the last one, we could just call this propanone because we only have one option for our double bonded O, because it's got to be on an interior carbon. That's my only interior carbon. But again, use the reference tables. So pause the video, try the other ones, and unpause it, and we'll go over it. So number 6, here's our functional group. So this is my COO. So this is an ester. So these are a little bit weird. The L points towards the alkyl, methyl, and then the other side has 2 carbons, eth, and then it ends in an OH, methyl ethanoate. Next one, OH, so I know it's an alcohol. Prefix for but, alcohols end in anol. Where's my OH? On the second carbon. So that's 2-butanol. Number 3, here's my carbonyl group on the end carbon. So I know it's an aldehyde. 4 carbons, but. Now, we don't need a number. Use table R, right? The example doesn't have a number, so we don't need a number. 4, here's our COOH, so I know it's an organic acid. So this is ethanoic acid. Number 5, here's my central O. So this is an ether. So we name the branches coming off of that O, methyl. So 2 are the same. We say it once and put a di in front. So this becomes dimethyl, and all ethers end in ether. So it's not methyl. It's just dimethyl ether. Number 8, here's my COOH, organic acid. 3 carbons is propanoic acid. Next up, here's my C double O on the end. So it's another aldehyde. So that's ethanal. And then my last one, here's my carbonyl group. It's on an interior carbon, so it's a ketone. So this is butanone. And now what's my number? 2, right? Lowest possible. Not 3, 2. There's no such thing as 3. So that's that. So if you did okay on all of these, you're doing really well. Remember, use table R as much as possible. If you're confused, go back, maybe watch some of the lesson a little bit more, and try and understand this as best as you can. But just remember, use table R. Everything is right in front of you. How to name them, how to draw them, how to identify them, and that's so remember, use table R as much as you possibly can. It tells you everything. If the example has a number, you need a number. If the example doesn't have a number, you don't need a number. And it shows you everything you need to do here, all right? And as far as identifying, though, it's in the condensed structural, most of the time it's here, right? So here, I can't draw on this. There we go. There's your OH, so look for that OH. Here's my OC in our ether, right? But now, sometimes when there's this double bonded O, it it's shown coming out of the top of the condensed structural. So you just got to kind of realize to bring that down, and then that becomes your CHO. Same thing here. We got to bring that double O down in the ketone to get our COC. And again, same thing with our organic acid. We got to bring that double O down to get our COOH. And then same thing with the ester. We bring that double O down, and it's going to be that Q, right? Ester says Q. And then the same thing with the amide. We bring that O down, and then we get our con, right? And then the amines, you're just going to look for an N. You see an N without an O, you know it's an amine. And the halides, you're just looking for a halogen. You see a halogen in there, you know it's a halide. So use table R. It's all right here.